Thanks, first of all, the organizers for inviting me to this always fantastic place, in particular when the weather is so fantastic. And I thank all of you that you have come here at this time of the day instead of going to the beach. And I also want to thank the organizers not only for inviting me, but for giving me the opportunity to give a little bit a longer talk, and but also for the fact that you have placed me in the program in such a place that I can refer to several people who spoke before me. So that was in particular the talk by Valérie Perrier. That was already quite interesting for me to see what is going on in the construction of divergence-free wavelets and how to use them. And Thomas, I also want to thank that he mentioned something about when we were PhD students. Actually, I started to write my PhD thesis in the area of wavelets for PDEs, and that was about 25 plus years ago that I started working in this area. My talk will be less perhaps than a survey, it will not be so much a survey talk about wavelets for PDEs, but it's rather a talk to see a little bit in retrospective what wavelets have given us for the numerical solution of PDEs. And I think it's also a good opportunity to try to condense some of the most basic features in order to give an idea in particular to the younger people here in the auditorium who don't have the experience of 25 years with wavelets, what wavelets are good for, what you can do with them, and what are still the problems that remain. And I also want to thank Jeremy that I met yesterday during a nice walking tour. He asked me, are there still a lot of people working on wavelets for PDEs? Well, there are less and less, and I can also explain why this is the case. Okay, so since I didn't know really what audience to expect, I thought I will start with what most people know about that wavelets have been used for many years, and initially in the context of signal and image processing. And the difference to a PDE is that a signal or an image is an object that is usually explicitly given, and it's described by a finite number of data points. And the original idea was to use data compression methods without losing essential information. Of course, they have been, fast Fourier transform has been around for many, many years. The JPEG package, the JPEG standard was based on that. And the essential method, or the essential idea of the method, was to when the object, so the signal or the image given in terms of data points, when it is usually the way it is given or the way it is plotted or described is in terms of a single fine scale that is that is kind of that also gives an idea about the complexity of the problem. So the finer the scale, the larger the number of data points is. And the method in order to achieve this goal is to perform a transform between the single fine scale and a multi-scale representation of the object. So once you have achieved this transform, you can look at the multi-scale representation of the object, and in the multi-scale representation you have information about essential parts and not so essential parts, detail coefficients, for instance, and then you can look at the detail coefficients and you can throw away some of them. The change of representation in order to achieve that is can be performed by what is called the fast wavelet transform in a pyramid scheme. And if you do that in a proper way, you can do it in an amount of operation that is proportional to n. And you can design such a fast wavelet transform if you have locally supported functions. And this is the fast wavelet transform in that sense is much faster than the fast Fourier transform, where you still have a log factor inside. And the fast Fourier transform, as everybody should have learned at some point in their studies, is based on the Fourier basis, which is not compactly supported. So if you have locally supported functions and you design this fast wavelet transform, you can perform this transform in an amount of operations which is linear in n, and this is actually also best possible if you have n given data points, so you cannot be faster. So once you have done that, you can discard small coefficients in the multiscale representation, and then you can look at the object of what you have achieved afterwards. And there have been, let's say in the 80s, there have been a number of people who have been trying to find such transformations which were, let's say, faster than the fast Fourier transform. But I think the breakthrough came when Ingrid Daubechies constructed her L2 orthonormal wavelets with compact support, and the paper came out in '88. I think many students still nowadays are, I would almost say, tortured by looking at this paper. It's technically, it's a very technical construction, and this is also perhaps one of the problems, one of the first problems why people were not so much interested, standard people from doing numerics for PDEs, why they were not so much interested in really looking at wavelets, because the fact that this is that you're using a sophisticated tool that, however, takes a lot of effort in understanding the construction. The people wanted to understand the construction, but they started looking at this paper, and then they figured out, oh, this paper is too complicated to understand. Personally, my idea about this is it's good to know that we have this construction. People looked at the construction, people have implemented it, and then we are ready to use it. But definitely this construction was a breakthrough, since it really gave wavelets with compact, provably compact support. Some very old examples that have been around. I think perhaps this was one of the first applications. It was interesting for me to go back to these old images. I think these kind of images people were using at the beginning of the 90s. This FBI finger, so this guy from working with the FBI doing the fingerprint. So here, for instance, you have, this is an original, this is a zoom of an original fingerprint. This is what up to that point used JPEG compression would give you by a compression of, let's say, 1 to 13. And what is very typical for the JPEG, which is based on the windowed Fourier transform, is that you see these windows here. And of course, if you make the compression even higher, then you always have these artifacts here. Well, once you use the wavelets, and I think this was based on the orthogonal wavelets, you get for about the same kind of compression, you get for the I norm a much better quality of the image. And that's why people consider this also a big advantage. So not only the fact that you could perform the transform faster than the JPEG, then the fast Fourier transform with Windows, but also the fact that the quality in the I norm was better. And then, of course, there was a company in Bremen in Germany, Mewis. They used that. They started using that also commercially in terms of, for instance, to compress X-ray images, also colored images. And this is a compression here of 80 to 1, so that means you really throw away a lot of the coefficients. And here again, you see the kind of effects of the working with windows in the fast Fourier transform as compared to a wavelet transform, a wavelet-based image compression. Well, when I look at an image here, clearly what we see here is an image is an object that lives on a finite dimensional space. That is an object that lives on a finite dimensional space, but it also lives on a finite domain. This construction by Daubechies, of course, is a construction that works with the Fourier transform. Like also we saw a lot of the construction of the frames this morning. All these constructions, they work with the Fourier transform, and by per se, you cannot immediately apply them to images that live on a bounded domain. So you have to do something about images, or you have to do something about bounded domains. And in images, it's not so, let's say, it's perhaps not so important what exactly you do at the boundaries. You have some boundary effects, of course. You can work with, let's say, you can work in periodic situation. Here you cannot work. This is not a periodic image, but somehow you have to do something at the boundary that usually the people don't talk about when they compress images or signals. But this is something that if you want to solve PDEs with that, that is definitely a very important thing, because the PDE, by definition, has the most interesting PDEs live on bounded domains, and they have boundary conditions also. So you have to do something about this. And actually, I'm not so sure about the wavelet toolbox that is, for instance, implemented in MATLAB. I think there are still not wavelets on bounded domains implemented there. I think they are still, perhaps somebody is working with this toolbox. I don't know. Anyway, yeah. So. And I will point out some of the difficulties, perhaps. So, okay, so if people say, okay, we compress an image here, so the image is really, let's say, an object, or a signal is an object in L2 on 0, 1, but let's say it's essentially treated as if it was an object in L2 of R2. And an image is let's say, as I said, is a finite dimensional object. More general, what wavelets give you, and this is an essential feature over other kind of, for instance, finite element approximations for PDEs. More general is that and this is what really makes it very nice to work with wavelets, is that if you want to consider an object in an infinite dimensional Hilbert space, then you can actually use wavelet basis for that, because wavelets in the original idea of the construction, wavelets is really a set for it is really a basis for an infinite dimensional space. So I want to start with the notion of wavelets that I have. I want to consider an object in an infinite dimensional Hilbert space on a domain, on a bounded domain RD. So this Hilbert space has an inner product, and this induces this norm. And what a set of wavelets for me is a wavelet basis, or wavelets is a set of functions psi. These psi's, they are in general indexed with an index lambda. Lambda is now here an infinite index set, and since I'm in several space dimension, this index comprises, for instance, the resolution on which this wavelet basis lives. So let's say, so this is the scale connected to the support. This is then a certain location, and in more than one space dimension, I have an additional index that tells me exactly what kind of basis that is. I have skipped that here because there are different possibilities to construct them. And what for me is a wavelet basis is there are three essential properties that make a basis a wavelet basis. The first, that is the basis for all types of compressions, is what is called norm equivalence. That means that this collection psi is a re-basis for this infinite dimensional Hilbert space. So that means that first of all, any object in this Hilbert space I can represent in terms of a linear combination of these functions, with the sum over all these indices. And what makes it a re-space is such that if I measure the V in the H norm, that is the norm that goes together with this Hilbert space, I can bound it from above and below, that I indicate with this tilde here, by the expansion coefficients in this basis in the little L2 norm. This looks like a, well, this looks like a property that is not that is perhaps not so important, but this property is really, let's say, the fact that you can represent an object in terms of a basis, and that you have full control with the expansion coefficients, that you have full control over this over the norm. This is the basis for doing all sorts of compression, and it will later also be used for error estimation. If somebody asks whether one can relax that also to frames, I don't care so much whether it's really wavelets or frames, whatever, as long as you have such a kind of relation. What is another feature which is very important in my context is that these bases that I work with, that they are local, so that they have a compact support, and the support shrinks as the resolution becomes finer. So if you think of, let's say, take this example here. So these are actually biorthogonal spline wavelets. So these are wavelets consisting of piecewise linear polynomials. So if my level of resolution, this modulus of lambda, if it becomes higher, then the support shrinks. The scaling means that also the let's say the H norm is kind of bounded, and the psi lambda means that these basis functions are centered around particular points, and the higher the resolution, the smaller are the supports, so that you can really in such an expansion that you can really use wavelet functions of higher level in order to for zooming in, for instance, along big changes of the function here. So this locality is a property that is important for PDEs because usually a partial differential operator is a local operator, and you don't want to really, without any necessity, you don't want to work with basis functions which are not compactly supported, which gives you in the end fully populated matrices. There's another property that is at the moment perhaps not so apparent that it is important. It is a cancellation property, also called vanishing moments. That means that if I integrate a function against a wavelet, if the function is smooth, then this integral vanishes, and this is you can see that, for instance, that's the reason why, for instance, you cannot have a function that is only positive like B-splines are. So after the initial construction of Daubechies, there came a paper by Albert Cohen, Ingrid Daubechies, and Fauveau, where they constructed biorthogonal spline wavelets, also using Fourier techniques. And we have worked with these constructions in order to construct biorthogonal spline wavelets on an interval, and then later on manifolds, and consisting of or decomposed in terms of patches, for instance. So there are by now there's an enormous amount of wavelet constructions around. Of course, my personal favorite are these biorthogonal spline wavelets, because I can work on the computational side. I can work with piecewise linears. These functions at the boundary, one has to make some adaptations here in order, of course, to have such a property on bounded domains. And the fact that, so on the computational side, I can work with, let's say, piecewise polynomials. And the biorthogonal means that I can, for this kind of basis, I can find a dual wavelet in which I can then represent these expansion coefficients. This is perhaps at the moment not so important. And whatever, so these three properties for me are really, really important. And they will come up in different contexts here. If you want to use frames, other kind of wavelets, okay, you can do that. If you give me a good construction on a bounded domain, you can, whatever I plan to do, you can do that here. What I would like to point out that I do not require any kind of orthogonality here, or orthonormality. So this L2 orthonormality of the Daubechies construction, in the case of PDEs, I don't have to assume that. I skip that unless you have something where an L2 inner product in the PDE appears. Then you could use it. There have also been people trying to construct wavelets adapted to inner products induced by PDEs. You can also do that, but then the construction again becomes complicated. Perhaps if you work with Fourier transform, then you cannot work again on a bounded domain, and so on and so on. So I just take let's say the simplest biorthogonal spline wavelets that I can work with, and no additional assumptions on orthogonality or so. Okay, so of course there's an enormous amount of PDEs around, and we saw, for instance, transport problems. We saw Navier-Stokes problems in the talk of Valerie. There is a large community of a larger community of people who are using wavelet transforms or local wavelet transforms for hyperbolic conservation laws, for instance, in order to detect shocks and discontinuities. There's also, in this era, there are some people working on what is called the spectral viscosity method, where you formulate hyperbolic conservation law in terms of a Galerkin formulation, where you use this kind of wavelet-based viscosity for stabilization. I don't want to talk about this. Oh, there's a typo here. Okay, apologize for that. I don't want to talk about this because here the idea is really, let's say, essentially it boils down to, again, using the solution that you have, for instance, for a particular time, applying locally the wavelet transform in order to see where you have discontinuities or where you have sharp gradients, and then using that in a sophisticated algorithm. But the idea of using wavelet transform is very similar. What I want to talk about is really wavelets as a multiscale basis for numerically solving PDEs, and a typical example is to work with elliptic PDEs. So for instance, I take an elliptic PDE of order 2R on a bounded domain. D should be larger than 2 to really have a PDE. In the case R equals 1, this is just a Laplacian operator with, let's say, directly zero boundary conditions. Or this also applies, let's say, I can also take the biharmonic operator. And what people usually do is you work with a variation of formulation. So you multiply with test functions, integrate over the domain. Then you arrive with an elliptic operator. For instance, in the case here of these two cases, you arrive with an elliptic operator, which is defined by the bilinear form that you can define from the left-hand side. In these cases here, you have, assume that you have a symmetric and continuous and coercive bilinear form, which means that, and you put the zero boundary conditions into the space. That means that your operator equation stemming from, so the weak operator form stemming from that has this mapping property. This mapping property means that the solution, first of all, the solution is unique, and it also means that you can bound the image from above and below by the function v in the Sobolev norm HR. I forgot to say that with HR here I mean the Sobolev space of weak derivatives up to order r. So in the case of the Dirichlet problem and the Laplace operator in this bilinear form, I just have the gradients inside. Okay, now when people use that by means of finite elements, what are the typical issues that appearing here? And people, if I look at the view from finite elements, so what people do is you take, for instance, a uniform grid. And the discretization on a uniform grid, you choose a finite dimensional subspace with respect to some grid spacing h, and you choose a basis, and then you can get a representation of the operator that is a linear system of equation that gives you this linear system of equations here. And the goal should be that you realize the discretization error accuracy, so that is given by this h, with a minimal amount of work in the amount of unknowns. So this would be, let's say, the best that you can hope for. But well, if you want to do a fast numerical solution, if you represent this space VH using a basis with compact support, for instance, a finite element basis, just head functions in the case of the Laplace operator, you end up with a large sparse linear system of equations. That means that you should use an iterative solver. But the convergence speed of the iterative solver depends on the spectral condition number of this operator A. And the standard discretization with finite elements unfortunately gives you that the spectral condition number is inversely proportional to h to the minus 2 over r. That means the smaller the h, the larger the spectral condition numbers. And I think in every numerics PDE class, the students, they should program in the beginning to set up these matrices and compute this spectral condition number and apply an iterative solver. If you want to have a high accuracy, you want to resolve singularities and so on, you have to choose even a smaller h, you get an even bigger problem and the condition number becomes worse. So this is the first issue, that this thing with the iterative solver. The second issue is whatever you do, you should think before what is the best that you can achieve. And this is given by a priori estimates for finite elements, and then a quality measure would be to approximate the solution with respect to a norm. I've chosen here, for instance, the L2 norm. So the idea is if you have a uniform grid, the dimension of your space is n, which is proportional to h to the minus d, then a priori finite element estimates give you an estimate like this, that the exact solution can be approximated with the Galerkin solution with respect to this coming from the space VH by the grid size h to the s, times the solution measured in the Sobolev space HS. Or when you rewrite it in terms of the number of degrees of freedom, you rewrite this in terms of n. For n degrees of freedom, this is the kind of accuracy that you can maximally expect. So the approximation rate is determined for piecewise polynomials of degree p, by the approximation order of your finite elements, by the space dimension d, and by the amount of smoothness of the solution in L2. Since I measure here in L2, here on the right-hand side I have this Sobolev norm. So the target is then to realize this discretization error accuracy for a fine grid with this spacing h to the minus, let's say 2 to the minus capital J. The problem complexity in d dimensions, I have 2 to the jd unknowns, and the optimal complexity of for an iterative solver is then capital O of n, so proportional to the amount of unknowns. So, so people have been doing that, of course, since, I don't know, 20, 30 years. But the issue is, if you now go to a multi-level setting, then you can solve some of the problems that I had on the previous slide. Namely, instead of just working with one space VH, I work with a multi-level setting of nested spaces, and my VH now corresponds to a space, a fine grid space V capital J. So. So the issue to overcome this problem with a fast numerical solver and this problem with the condition number, this is the first issue, or this is the first, let's say, appearance of wavelets in the context of numerics of PDEs, aside from using ad hoc approaches, perhaps to use a little bit. Well, I say this was perhaps the first really systematic appearance of wavelets in the context of numerics of PDEs, and I think the first paper was Stéphane Jaffar. He used Meyer wavelets for preconditioning the elliptic operators, and the way it worked is the following. If you set up your stiffness matrix with respect, so this is the matrix with respect to the space V capital J, the idea is that you find a linear operator that I call Cj, that is called a preconditioner, in such a way that the spectral condition number does not depend on J anymore, but of course the setup and the application of the Cj should be optimal linear complexity. I mean, of course, you don't want to take the inverse of the Aj. This would not be of optimal complexity. These multi-level schemes, and that was the spirit, let's say, of the end of the 80s, beginning of the 90s. There were already multigrid methods around, and it was the idea to use wavelet or wavelet discretization, or to use preconditioners based on the fast wavelet transform. This was used systematically first by us here in order for preconditioning these operators. And the relevant idea from approximation theory here is that you take a multi-level characterization of function space, which you can do in terms of wavelets, and combine it with this mapping property, this that I had before when I defined this operator. So you combine this mapping property with the norm equivalence. If you have these norm equivalences, and if you have the right properly scaled basis there, then this is just a one-line proof. So, so that means if you use and there have been variants afterwards. So if you use a multi-level preconditioner, and I think we will also have multigrid appearing here. If you use a multi-level preconditioner that is based multigrid, or BPX is a kind of frame version of that, or if you use wavelet discretizations, then your condition number, your spectral condition number, is independent of the grid size. And if you use that together with nested operation, with nested iteration, then you can really show that this is an optimal solver. Okay, but this is, let's say, this optimality of the BPX preconditioner. This is perhaps an interesting thing just to mention to the students here. Imagine, so there were Bramble, Paschak, and Shu. Before there was this hierarchical basis preconditioner by Iserentant, where he was able to prove that this using a hierarchical basis gives you a better condition number than just using a fine scale basis. Then Bramble, Paschak, and Shu, they had this idea to use a kind of scaled frame construction, and they observed that the condition number was uniformly bounded independent of the grid, but they could not prove it. and they were very frustrated. This paper that came out here, it shows these optimal condition numbers, but the kind of argument that they used in order to show this something about this preconditioner was not good enough. You really had to go through to approximation theory in order to prove that, and that was actually quite nice a nice application of these norm equivalences. But here, this kind of thinking, let's say, so coming back to the methodology, this kind of thinking is really, let's say, from the point of view of finite elements. So you have used finite elements before. There were some problems where you could not prove certain results in terms of finite elements, and with the new tools, namely these norm equivalences, you were able to do that. But if I now want to go beyond the view of finite elements, so not only mimicking finite elements, but really trying to do something, what wavelets can give me on top of that, I should really go perhaps away from this finite dimensional situation, so starting with a finite dimensional subspace, namely since I have a basis for an infinite dimensional function space, I can think of representing infinite dimensional objects, and the operator equation is an infinite dimensional object, or the solution is infinite dimensionally. I can use that in order to represent infinite dimensional objects and implicitly given objects given in terms of as a solution of a partial differential equation. The reason why I put up these things about the preconditioning is that if I use properly scaled wavelet basis, properly scaled means that already the condition number is good, and I represent my elliptic PDE in this form, I can use these bases also for adaptivity for smooth solutions. So for non-smooth solutions. So that means that the norm equivalence serves several purposes. It gives me a well-conditioned problem in little L2, where I don't have this condition number problem anymore. And then I can also use a norm equivalence for adaptivity, because of course I cannot put an infinite dimensional object into the computer. Okay, so in that sense, this idea was systematically formulated, and that's why I would call it a paradigm, in a series of papers by Albert Cohen, Wolfgang Dahm, and Ron DeVore about 10 years later. And once you have seen the idea, you will think, well, this is really nice. So you start out with a well-posed variational problem, so a kind of operator equation by equals f. Well-posed means that you have this mapping property that I showed before for the elliptic case. And you don't have to work with a Hilbert space and its dual. You can work here with different kind of Hilbert spaces with different norms. Once you have a wavelet basis for these spaces appearing here that satisfy each of them a norm equivalence, you can represent this operator equation in terms of these wavelets. Then this operator equation is a well-posed system in L2. It's still infinite dimensional. The mapping property and the norm equivalence, this is exactly what gives you these optimal condition numbers. And now you have systems in little L2 where you can control with these expansion coefficients, the expansion coefficients of the operator applied to that. And then, of course, this is still in an infinite dimensional system. You have to make you have to design practical solution schemes, and there are by now also different kind of solution schemes. There is, for instance, one that is just based on a Perturb-Richardson iteration for the symmetric case. You know that the scheme converges, and in order to apply this operator, you can use an adaptive evaluation of this operator applied to an input vector, and then you can, for complexity reasons, you can you should coarsen or threshold the iterants. And there's another type of direction adaptive wavelet Galerkin methods and bulk chasing strategy. So let's say in the last 10, 12 years or so, people have been working also on these methods. What makes it interesting is that there's let's say one fashion in PDEs also in the last years working with space-time variational formulations, in particular for evolution PDEs. And there the idea is, so instead of using a scheme for an evolution PDE to march forward in time, the idea is to write also this kind of equation, so a kind of parabolic equation, to integrate again with respect to t, with respect to time, and then integrate also on the time interval, so that you end up again with an operator equation where now the time and the space variables are also inside this operator here, and then you can apply the same machinery as before. The difficulty here with this space-time formulation is that you have to find the proper solution space in order to come back from this full weak space-time formulation to this original formulation. But so this goes back, actually, I learned to a paper by Ladyshenskaya already. Daudet-Lyon and Schwab and Stevenson have used it in the context of wavelets. Okay, what is nice, I must say, I think I talked too much at the beginning. Now I'm running out of time. I have less than 20 slides, but okay. Perhaps what... I have less than 5 minutes, okay. There's 1 hour for the posters. Okay. What is nice in this context here, and this is something that has not been in that sense up to that point without wavelets one has not been able to prove that in terms of finite elements or other discretizations. Namely, you can do a complexity analysis, and the complexity analysis tells you that you can achieve the same work accuracy balance of best n-term approximation as if you knew the object already. So I mentioned at the beginning this example of the image compression. So there the image was given explicitly. You apply the wavelet transform and then you throw away small coefficients. This is if you use a good wavelet transform, this is a O of n construction. Here you can do a very similar. You can achieve a very similar result, namely that also for target accuracy epsilon, you can achieve you can achieve that target accuracy with optimal work. And this is a situation, for some reason, this is a situation where these vanishing moments for the wavelet essentially come in. I mentioned before that this is a very important property. So this operator, this infinite dimensional operator, with this you can show that this is compressible, and then you can design solution schemes that you achieve for every epsilon, that you achieve your accuracy epsilon, and that also if you have if your solution is in a particular space that has decay S for the wavelet best n-term approximation, you also have optimal complexity. Okay, here I wanted this is the last, let's say, results, how to apply nonlinear operator in wavelet basis, how to actually implement that, and where the compressibility and the moment conditions come into play here. I have a PhD student, Roland Pavel, who has implemented that in arbitrary space dimensions, and the main idea is to work, you can work with nonlinear operators on the tree-type index sets, and then you compute the application of the operator to a given vector after transformation to piecewise polynomials, and therefore you can apply this in optimal linear complexity. This is an example where this full weak space-time formulation was used. This is an example to show that this implementation of the nonlinear operators works up even to 4D in optimal complexity. And then I wanted to talk a little bit about control problems with PDEs, but I'm afraid I will have to skip that. These weak space-time formulations are particularly interesting, and particularly interesting is also that you have here a system of PDEs where you have a state of the system. By the optimal control part, you get a co-state and also a control. And if you have such a system of PDEs, it's interesting how you do adaptivity. So you still have this problem of in each time step to solve an elliptic PDE. If you do time stepping, if you do adaptive finite elements, the question is how do you choose the meshes for the different variables. And here we also have a good, let's say, approach to use the full weak space-time form, set up the control problem in infinite wavelet coordinates, and then you can also prove these kind of optimal complexity estimates, which is a little bit more messy because now you have 3 variables, a coupled system of PDE, but it's okay. This is an example to show that it makes sense. This is the state, the co-state, and the control, and it makes sense to use different meshes for the different kind of variables. Okay, so the question is beyond wavelets. So what can you do? Well, the preconditioning you can do by using other kind of multi-level and multi-grid methods. About error estimates, convergence theory for adaptive methods for instance, space-time formulations. I'm not aware of, for instance, optimal complexity estimates. The question is, as soon as you have a coupled system of PDE, what do you do, one mesh or different meshes for all the variables? If you want, definitely for optimal complexity, you should have different meshes, but then you have to transform the different variables from one mesh to the other one. Complexity estimate in terms of finite elements, I'm not aware. Also convergence theory of adaptive finite elements, DG methods for control problems, this is another issue. And I would wish, so let's say, and there are several other objects that come up here. For instance, if you do convergence with respect to another error criterion, another quantity of interest is interesting. What do you do? Usually you might also have additional inequality constraints. How do you do that? And let's say my take-home message, I forgot to say, also in isogeometric analysis, we heard already some talks of hierarchical basis in the context of isogeometric analysis. I think there it would also be interested to have, let's say, kind of wavelet constructions in order to do perhaps error estimation. And the take-home message is, for me, is not only try to copy what you can do with one method a little bit better than with another method, but really think about what is the best that I can achieve, or what is like, make a wish list first of the kind of equation that you want to solve, and then think about what is a good construction. We are going, actually at the moment, we are going back to the construction of B-spline wavelets on intervals, trying to optimize some of the constants there, and also to have some B-spline wavelets in future for higher order polynomials available, because I think this will be one of the big issues, how to do error estimation and local refinement, and having good basis for that.
Thank you very much. There's still time for one or two quick questions.
How do you solve the infinite linear system?
Well, this is so I try to indicate it here a little bit here. So here you design a routine. Here perhaps so you design a routine where you you start out with an idealized iteration. You start out with an initial vector of compact support, and then you approximately realize the application of the operator to the right-hand side up to accuracy epsilon. So your routine will be a finite dimensional routine. Of course, you cannot do that. But if you do it and you have to do it in such a way that, and this is something where your vanishing moment come into play, because then you know, since this is a PDE operator, you know that if you apply a PDE to a finitely supported vector, it will not spread too much. So perhaps I can explain that here. Let's see here. Okay. So if you work, for instance, on a tree-type index, there's a lot of machinery behind. I mean, it's not so obvious. It's not so trivial. So you start with an input vector. Your input vector only has finite indices. Then, based on this tree and based on the support and the properties of your operator, you can predict how far this tree will spread. And then on the tree, you compute the application of this operator applied to this input B. So this is, let's say, what is condensed in these three lines here is about 50, 60 pages of not so easy implementation, but it's doable, yes.
Okay, so I think we have a poster session ahead. So let's thank all the speakers of this session again.